Unified dynamics. Distinction theory.
The center of this image holds one of the most stubborn mysteries in modern physics. We understand the glowing ring of superheated gas, but the black void in the middle represents a total breakdown of our current laws. General relativity models the core of a black hole as a singularity, a point of infinite density where the fabric of space and time curves infinitely back on itself. This prediction creates an intractable conflict with quantum mechanics. If mass and data fall into a mathematical pit of infinite density, the laws governing the conservation of information are violated. Albert Einstein recognized that these singular endpoints signaled a limit where his equations stopped describing reality. The singularity appears to be a mathematical artifact, a consequence of assuming space is a perfectly smooth, continuous manifold rather than a discrete structure. The unified dynamics framework replaces continuous fields with a discrete, computable structure. Space-time is modeled as a purely combinatorial ledger, where the movement of energy and matter is governed by rigid network rules. The foundational building block is the K4 tetrahedral graph, a minimal volumetric structure consisting of 4 nodes connected by 6 structural edges. Theorem 572 demonstrates that an event horizon is a manifestation of an algorithmic capacity ceiling, a hard limit on how much information the network can process in a single region. Replacing the continuous manifold with this capacity-limited graph allows us to derive the event horizon and resolve the information paradox using pure combinatorics. In this framework, space manifests as a network of unexecuted computational updates. Data packets travel along the 1D edges to achieve topological relaxation. When packets accumulate faster than they route, the node experiences a backlog called processing burden. The K4 geometry dictates an absolute limit to this density. If exceeded, the system experiences structural lattice shear. This vertex information capacity limit is fixed at the fraction 7/768. This value exists as a rigid structural invariant of the graph itself. It is derived from the total state space of the tetrahedral cell, rather than being tuned to fit observations. Under standard loads, the processing burden remains safely below this limit, allowing the network to function as a predictable linear medium. As the burden approaches the threshold, the node experiences escalating latency and structural strain. Hitting the limit causes the local graph coordinates to go completely bankrupt, meaning the node can no longer accept or route standard linear updates. This algorithmic cap places a mathematical floor on the system, preventing the formation of infinite density by denying any single point the capacity to hold it. To map the point of gravitational collapse, we use the variable m to represent the number of overloaded edges intersecting at a single vertex. Gravitational compression forces multiple tetrahedral cells to share a single node, driving the intersection toward its breaking point. At 10 overloaded edges, the vertex is operating at 95.2% of its absolute information capacity. Data trajectories are highly distorted by this congestion, but the node remains technically functional. Packets can still trace a path through the strain. However, a discrete graph cannot support fractional edge connections. The critical breach occurs with the addition of an 11th edge. This 11th connection pushes the burden to 11/1152, which strictly exceeds the capacity ceiling of 7/768. To maintain global solvency and prevent a cascading system crash, the network executes an immediate localized quarantine. The local admissibility field drops to 0, effectively closing the gates to any new inbound data traffic. Simultaneously, edge impedance spikes to infinity. The paths used for standard linear routing are now physically locked. All linear routing permissions through this coordinate shell are revoked. This frozen, zero-liquidity data zone creates the effective surface that an outside observer identifies as a black hole event horizon. While linear edge routing is paralyzed, the foundational conservation of information remains in effect. The 5-component carrier state of the data must be conserved, even if the primary pathways are blocked. The network resolves this by engaging a topological relief valve, the homological co-boundary operator. The backlog bleeds orthogonally outward through the 2-dimensional triangular faces bounding the vertex. This redistribution is dictated by the anisotropic co-boundary transformation matrix. The first row applies a 3/4 dilution factor to mass density. The second row expands phase volume by 4/3. These two factors perfectly offset each other, ensuring the total integer count of the information is algebraically conserved. The closure and framing channels remain unchanged, passing through as identity invariants. These invariants maintain the horizon boundary as an absolute gauge singlet, appearing static. The final row provides the escape mechanism. The boundary integrity component flips its sign. Normally, this keeps data contained, but inverting it while internal pressure peaks forces the ledger to resolve outward. This matrix serves as the engine of survival, converting a bankrupt storage register into an active emission channel. When we apply the results of this matrix to the macroscopic scale, we see the frozen boundary is not truly static. This algebraic output, the term pi c rho minus cb, unmasks the geometric origin of black hole evaporation. The energy of the trapped packet is not lost to a singularity. It is simply denied its original path through the network. The capacity limit forces that energy to leak across the two-dimensional face boundary of the horizon. We define this process as sub-threshold evanescent face bleeding, a continuous redistribution of the internal burden. This discrete process identifies the physical source of the thermodynamic radiation proposed by Stephen Hawking, resolving the paradox through pure geometric necessity. Gravity emerges as the geometry of a discrete algorithm managing its own computational debt, ensuring that information is conserved even at the edge of the void.